So we're going to talk about Le Chatelier's principle. So what happens in Le Chatelier's principle is if we are at equilibrium, what happens if we stress that equilibrium? Meaning, what happens if we add reactant, or we change the pressure, or we change the temperature? We're going to have to reestablish equilibrium, and the question is, how exactly do we do that? Is there going to be a shift to the right to make more products, or is there going to be a shift to the left to form more reactants in order to reestablish equilibrium? So, the first change that we can force is changing the concentration at equilibrium, okay? So, if I give you this reaction here, I could change any of these concentrations. These reactants and products coexist, so you'll have carbonic acid, carbon dioxide, and water coexisting in a solution. So, the question is, what happens, for example, if I were to add H2CO3, what would happen if I added CO2, or what would happen if I added H2O? And the answer is, if you think about it, if you suddenly add more reactant, what that means is that the rate of your forward reaction is going to increase, meaning you're going to form more CO2 and more H2O. So you would shift to the right. If I increase my concentration of CO2, however, my reverse reaction would speed up, which means I would form more H2CO3. So wherever you see an increase, okay, it's going to go in the opposite direction of that. While if you have a decrease, like if I have a decrease of H2CO3, that means I would see a shift to the left. If you want to imagine just the everyday example of like a party, for example. So if these are two different parties, right, and people are moving from one party to the other, if I suddenly have a bunch of people on my reactant side and at my reactant party, what that means is that there's going to be a shift and a number of people are going to move over to my product party, and then equilibrium will be reestablished. So let's look at these examples. So if I add H2CO3, I'm going to have a shift to the right. If I add CO2, however, I'm going to see a shift to the left. And if I removed H2CO3, I'm going to have a shift to the left.
So the question becomes, how can we actually change concentration? And so there are the obvious ways to change concentration. For the example that we just looked at, you can add carbon dioxide or remove carbon dioxide. You can add water or remove water. You can add carbonic acid, you can remove carbonic acid, but are there other ways to change concentration? And the answer is yes. You can in fact add substances that don't exist in your equilibrium, and those substances can actually affect the equilibrium and cause a shift. So let me show you how. So specifically what I'm going to be talking about is how we can decrease concentration. And how we can do that is one way is we can form a precipitate, okay? So if you look at this equilibrium right here, you've got lead nitrate, and it's breaking apart into lead ions and nitrate ions. So it's in equilibrium right now. So how could I cause a shift either to the right or to the left? Well, one thing I could do is I could add NaCl, and that's actually going to cause a shift to the right. So let's look at why. Because if you notice, NaCl, sodium ions, Na+, and Cl- do not exist. Neither of those exist in your equilibrium, and yet that is going to impact your equilibrium. So let's talk about how. Well, what happens is that sodium ions are always soluble, so they're not going to have any sort of an impact on your equilibrium. But chloride, Cl-, can form a precipitate, and if you notice, chloride has a negative charge, so it can form a precipitate with a positively charged ion, which in this case is lead. So since chloride and lead can form a precipitate, it can form PbCl2, what's going to happen is that PbCl2 is going to become a solid, removing lead ions, Pb2+, from the solution. So since you're removing the lead ions from solution in order to form a solid, that causes the concentration of lead ions to decrease. And since you're decreasing the concentration of lead ions, that's going to cause the entire system, since the concentration is decreasing on the product side, to shift to the right. Okay, so that's one way. You add something that seems to have nothing to do with equilibrium at all, and yet it can in fact affect the equilibrium, specifically by forming a precipitate. So just for people who are more visual learners, you can actually see in this diagram here, imagine this used to be a solution that had lead and nitrate in it, and by adding the sodium chloride, the chloride ions and the lead ions will form this lead 2 chloride precipitate, that white precipitate, lead chloride, removing the lead ions from solution, causing its concentration to decrease, and therefore causing a shift to the right. The other way to decrease concentration is to allow an acid and a base to react. So let's look at that. Here is another equilibrium, lead hydroxide, and it produces lead ions and hydroxide ions. Okay? Remember, hydroxide, OH- is a base. So what we could actually do to remove hydroxide is we could allow it to react with an acid. Remember, when an acid and a base react together, they form water. And so I could add, for example, HCl or any acid, HNO3, whatever acid you want to add. And what happens is that the H plus from that acid will react with the hydroxide to form water. Well, what does that do to your concentration of hydroxide? Well, it causes your concentration of hydroxide to decrease, causing a shift to the right. So just as I had explained before with respect to concentration changes, the only thing new here is I'm forcing you guys to figure out, okay, how does the addition of a seemingly completely irrelevant compound like sodium chloride or hydrochloric acid, how can the addition of that to my equilibrium actually cause a shift? And the answer is it can potentially form a precipitate, or you could have an acid and a base reacting. Now, keep in mind, you're not required to memorize your solubility rules, so there would have to be some sort of a hint that lead chloride would form a precipitate. Okay? You're not expected to have that memorized.
All right, so that's concentration. Well, what happens if I change pressure or volume? Okay, so let's look at this example. Okay. You need to write a note to yourself. If you increase pressure of a system, then you're going to shift towards the side that has fewer moles of gas. Okay, so increase pressure, you're going to shift to the side that has fewer moles of gas in order to reestablish equilibrium. So if you look at this, my reactants, I've got 1 mole of N2 and 3 moles of H2, which means I have 4 moles on my reactant side and only 2 on my product side, which means if I increase pressure, I'm going to see a shift to the right. However, if I decrease pressure, it's the exact opposite. If I decrease pressure, I'm going to shift towards the side that has more moles of gas, so I would shift to the left. Now notice I also included volume. Keep in mind, pressure and volume are inversely related. So if I increase pressure, that means I decrease volume. So if I ask the question, what would happen if I decreased volume? In your head, what you have to do is say, all right, if I decrease volume, that means I increase pressure. And if I increase pressure, I'm going to go towards the side with fewer moles of gas. So I'm going to go towards the right. So you can do it for moles, you can do it for changing volume, or you can do it for changing pressure. Keep in mind that everything involved, whenever you're working with this, you need to be just looking at your gases. So notice I said 4 moles of gas and 2 moles of NH3. If N2 were, for example, a liquid, I would only have 3 moles of H2. I wouldn't have 4. So make sure everything that you're counting for moles of gas are actually a gas. The last thing, effective changing temperature. So if you look here at my reaction, notice heat is on my product side, which means that this reaction is exothermic. If it were endothermic, then it would be on my reactant side. All right. Now, all you have to do for increasing heat or removing heat, just treat it like you're adding a product or removing that product. So if I were to increase heat, imagine increasing the concentration of a product, you would see a shift to the left. While if you removed heat, right, you're removing a product, then you're going to see a shift to the right.
Another way to say that, instead of saying you're adding heat or you're removing heat, you can simply say I'm increasing the temperature, that would be adding heat, or I'm decreasing the temperature, I'm removing heat. So if you're increasing the temperature in this example problem here, if you increase the temperature, you're increasing the heat, that would cause the shift to the left. If you decrease the temperature, then you would see a shift to the right. So now that we've talked about how increasing or decreasing temperature affects your equilibrium, one thing that I mentioned was heat being on the reactant side or heat being on the product side. Well, that begs the question, how do we actually determine where that heat is going to be? How do we determine if it's going to be a reactant or a product? Okay. Well, if you have an endothermic reaction, remember an endothermic reaction is one in which energy or heat is required. Okay. It's an input, you have to put in heat. Okay. Your heat is actually going to be a positive value. So if the heat value that you're given is positive, you know that you have an endothermic reaction. Okay? In an endothermic reaction, because heat needs to be provided, heat is going to serve as a reactant. So if I give you a positive heat value, or I tell you that a reactant is going to be positive, then heat is going to go on the reactant side, on the left-hand side, which means increasing the temperature would cause a shift to the right, and decreasing temperature would cause a shift to the left. If instead the reaction is exothermic, then the heat value is going to be negative, and that's because heat is being released by the system. Okay? So the reaction is releasing heat. The heat value is negative because heat is being lost. And since heat is being lost, we represent that as heat being the product. So if you're ever given a heat value that's negative or told that the reaction is exothermic, then your heat will serve as a product, in which case increasing the temperature will cause a shift to the left, and decreasing temperature would cause a shift to the right. All right, question of the day. We've been talking about shifting, okay? And the other concept that we looked at previously was your equilibrium constant. And that begs the question, okay, does the equilibrium constant ever change when we're talking about these shifts? And the answer is sometimes. So if you have a shift that's caused by a concentration change, your equilibrium constant will not change, okay? Your equilibrium will be reestablished. Your equilibrium constant will remain the same. If you have a shift that occurs because your pressure or your volume changes, your equilibrium constant will not change. It will simply reestablish equilibrium, and the equilibrium constant will be the same. However, if you change temperature, right? If you increase or decrease temperature and have a shift as a result, then yes, your equilibrium constant will not change. So let's look at how exactly it will change. Well, if you remember, the equation for your equilibrium constant, the way we determine it, is by taking your products, multiplying their concentrations together, right? Dividing by the concentration of reactants. Okay? So it's products over reactants. So keep in mind, if you increase the amount of products, that's going to cause KEQ to increase. If you increase the amount of reactants, that's going to cause KEQ to decrease. So if you have a shift to the right, when you're shifting to the right, that causes your concentration of products to increase. And if your concentration of products increases, that means your KEQ is going to increase as well. If instead you have a shift to the left, your KEQ will decrease. So keep in mind, this increase and decrease of KEQ only applies if you are changing temperature. If you have a change in concentration or a change in pressure or volume when you're dealing with a gas, regardless of in what direction the reaction shifts, your KEQ will stay the same. It will remain constant.